Alrighty, so let's share the screen. So this question, right? So we're converting
Yes.
Cartesian
Yeah,
to
yeah, it says convert from rectangle to polar coordinates, and I understand the gist of it. And then when it comes to like number C, where it goes from
yeah.
like -2, and that part where I'm changing the arctangent, which is going to be 2 over -2, which gives me -1, and then how it correlates -1 to I think it was pi over 4. Yeah, pi over 4, negative pi over 4.
Um, okay. Let me run through a couple of these. Let me get the right camera going here.
Yeah, the -5 over 5 would be the same.
Okay. I'm playing with my light here. There we go. So the basic idea, I'll start with an easy one, this 9, 0. If you plot it, it's this point right here. So the R is the distance from the origin.
Yeah.
So this is going to be 9. The theta is going to be the angle above the x-axis.
And since there's no angle, it just becomes 0.
Yeah, so ironically, it's the same point. 3 and then 3 over rad 3. So I'll just kind of eyeball it. Now 3 over rad 3, I mean, I don't need to be exact, but I want to get close. About 1.732. All right. For the distance, you just do a Pythagoras theorem. You get 9. This one gives you 9 over 3, which is 3. So it's rad 12, which is the same as 2 rad 3. You can leave it as rad 12. The theta is going to be okay, so here's your arctangent question. It's going to be the arctangent of the top divided by the bottom. Okay. Give me a second here. So you need to reduce this. This is just kind of ugly here. It's actually, so 3 over rad, this is actually just rad 3. 3 over rad 3 is the same as radical 3. Um, hold on.
Yeah, it becomes
That's
just
just
rad
rad
3 by
3.
itself.
So now I guess we should just remember, do we remember our, oh, this is a common form. This is 1 over rad 3. Um, so this is where you bring in your trig days. Do you remember that angle?
That's a part of that. I guess I have to go back and
Yeah. I'm
review.
gonna, you know what? I don't remember it either. So what I'm gonna do is I'm gonna draw up a table here. This is the old sine, cosine, tangent. We'll have this for reference. So 0, pi over 6, pi over 4, pi over 3, and pi over 2. So the first quadrant, the sine is there, they count up. The cosine counts down. Tangent is just a stacked sine over cosine, so 0. It's going to be 1 over rad 3. That's going to be our answer right there. This will be 1, this will be rad 3, and this will be infinity. All right, so sorry, I'm running a little fast here, but so the arctangent of 1 over rad 3 is going to be pi over 6. So that would be your r theta would be 2 rad 3 comma pi over 6. Does that make sense on that one?
Yeah, I'm seeing it, Professor. I'm seeing it.
Okay, so now this is all in the first quadrant. this guy is not in the first quadrant. We're gonna have to goof around with it a little bit. It's actually in the second quadrant. It's gonna be -5, and then 5 up. As far as the R is concerned, this one's just in the way. As far as the R is concerned, it's not that hard to do. We'll do it real quick. Square away any negatives. You're going to get 50. So 25 and 25 is 50. So that's 5 rad 2. All right, here's the problem if you depend on your calculator, is that when you type in arctan -5 over -5, which is arctan of -1, um, in fact, I'll do it on my calculator. I know I'm going to get the wrong answer. So I'm going to type in arctan -1. Oops. Yep, I'm going to get into degree mode. It actually gives me -45 degrees, which puts me in the fourth quadrant. So you have to be aware that the arctan gives answers in quadrants 1 and 4. If you just use your calculator, it's just going to spit back answers either in this quadrant number 1 or this quadrant number 4. So what we need to do here is, well, there's a couple things. I actually just draw out the picture. The answer that it gave me when I typed in arctan -1 was -45 degrees, which is this angle down here. But I actually want this angle up here. So one thing I can do is I can add pi to that. So for example, so -45 degrees is -pi/4 radians plus pi. So this actually adds half a turn. This puts us in quadrant 2. So pi plus a -pi/4 is going to be 3 pi/4. And that's going to be your theta. So your R is 5 rad 2 and your theta is 3 pi/4.
Okay, so if I'm getting this right, what I'm doing is I'm not adding anything. It's just adding pi puts me on the reciprocal side of -45 degrees to just 135, which makes it 3 pi/4.
You need to determine which quadrant you're in. And then you need to make
Got
sure
it.
that whatever the calculator gives you, you need to adjust that to put you in the right quadrant.
Got it, Professor. Thank you.
Yeah,
I see what you're saying. If it was quadrant 1, then -pi/4 would have just been converted to just pi/4 by
right.
adding.
Yeah, if the ironically, if the point was 5 comma -5, that would be down here. Then yeah, you'd be done because arctan of -1 is -pi/4. Actually, even then, I noticed that infinity wants it with a positive theta, so you'd have to actually go the long way around. So
Got it.
you'd have to go, okay, well, -45 degrees is the same as going all the way around 315 degrees, or what is that, 7 pi/4? That help?
Got it. Yeah, thank you, Professor.
Sure. All right. Hey, so here we go. Um, Summer 2024. So long ago. So any question, which question would you like to look at on this one?
We could just do number one.
For the parametric curve defined by what you see there, algebraically find the equation of the line tangent to the curve at the point corresponding to t = 1. Find all values where the tangent line to the graph of the curve is horizontal. All right, let me just copy it. So this is x is t to the 4, take away t, take away 3. Y is 3 natural log t. And I'm assuming that the remaining stuff is outside of the ln. That's not actually clear. So in other words, I'm assuming that the t here, right after the natural log, is the only thing inside the natural log. So I'm going to go with that. So I want the equation of the line tangent to the curve at t equals 1. And then I want where the graph, the tangents are horizontal. Alrighty. I see Shannon's remark. I'll get to that one in a bit. As far as setting up the derivative, so we want dy dx. What we're going to do is we're going to go dy over dt over dx over dt. So dy dt is going to be 3 over t, take away 2t. And on the bottom, it's going to be 4t cubed, take away 1. So that's the derivative. So the slope at t equals 1 is just to plug in t. We get 3 minus 2 on top, 4 minus 1 on the bottom. That's what, 1 over 3. The point is you plug in 1 up to these guys. So you 1 minus 1, that drops out, minus 3, so you get negative 3. And then ln1 is 0. That's gone. We have negative 1 plus 3 is 2. So then in this case, we just do our old friend from algebra, y minus 2 equals slope times x minus negative 3, so x plus 3. All right, so that's how you find the equation of a line. We want to find then where the tangents are horizontal. So the tangents are horizontal where dy dx is 0. So that's the same as setting the top to 0. Oops. So I go 3 over t minus 2t equals 0. And I just got to work that out. So if I get multiply 3 by t, I get 3 minus 2t squared equals 0. So t squared is, what's that going to be? 3 over 2. So t is going to be plus and minus radical 3 over 2. I think that's all it wanted. Let me go back to the question. Yeah. Okay. Yep, it worked. All right. All right. So that's how you do the first one. Shannon had a question in the chat for 9-2, number 2. You're thinking it may be the wrong answer on the sheet, so let's take a look. So before I do that, does that help with this question?
Yeah, it does.
One thing I want to mention is that when you're looking for where the tangents are horizontal, you set the top to 0. You have to actually have to also make sure that it doesn't make the bottom 0. These are good. Sometimes you might get a case of 0 over 0, in which case actually those usually turn out to be cusps. Those are little corners. In this case, these values here will not make the bottom 0, so we're safe. All right, so let's take a look at number 2 on that same sheet. I'm going to share the screen again. Alrighty, what we got going on here? Number 2, for the parametric curve defined by x is 8t net plus natural log t, and y is 9t plus natural log t. I'm going to skip part A. I'm going to go right to part B because I think that was the question you were asking about. Find all values of t where the tangent line is horizontal. So to remind you, when you're setting up the derivative, dy dx is the same as dy over dt over dx over dt, which dy over dt is going to be 9 plus 1 over
I think
t.
that's supposed to be a minus natural log of t.
Let me double check that. Yeah. Oh, yeah, you're right. the minus. There we go. So it's going to be 9 minus 1 over t. I'll just go ahead and write the derivative for the bottom one. What the hey. All right, so we set the top to 0. And I just got to solve for t. So I'll bring the 9 over. That's going to, or actually bring the negative 1 over t over. So that's 9 equals 1 over t. So t is 1 over 9. And that's what you said. And what does the key say? I'm going to find out.
The key just has the same answer as your 1b, so I think that was
Oh,
just a typo. Then
yeah. All right. Well, that's funny. Yeah, it's not funny. That's a typo. Okay, you are correct.
Professor, let
Uh,
me just say you are doing it way faster than it takes me.
okay. Well, if I need to slow down, you can always interrupt me. You can always you know have me slow down. I am kind of going through some of the algebra quickly, but
No,
I'd
I
be happy.
definitely see it. It was just I mean, obviously you've done it before, so the fact that you just like bam, 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 like okay, cool. I have to remind myself what the next step is. But thank you, Professor.
Well, it's a lot of practice. That's what it boils down to. Um, so you are correct that this is the correct answer for 2 part B on that review sheet. Um, yeah, it's obviously just copied and pasted the other thing and then change it. All right, if anybody wants to take an image of this, again, it's not the best image, but go ahead and do so. Now, I sent out on ed discussions showing you how you can do this on Desmos. Has anybody been doing these graphs on Desmos? I think I think you should. It's kind of fun, and you can. It'll also help, I think, answer some of your questions. Some of the questions like, "What does this graph give?" And just graph it, take a look. So,
Yeah, I have a question about using it on Desmos. I have been using it on Desmos to graph these functions.
uh-huh.
The only thing I noticed the difference is it doesn't give me like intersection points like it does with like just f of x or y equals or x equals when you have multiple.
Okay, it's very
Is there a way to
possible.
do that?
One of the problems with graphing in parametric and or polar is that you actually get where you can actually have situations where they physically cross, but algebraically you can't solve for the t where they cross. It's kind of like a spurious crossing. Um, I wonder if Desmos just simply turned off that feature. Um, I'm trying to think of a good example where it does that. I can't off the top of my head. But yeah, it may have turned off that feature. You know, on any of these questions here, you just graph them. I mean, it's going to look kind of bizarre, I would imagine, but um, at least it helps you kind of see if your math is kind of agreeing with the picture. That's always a good feeling. And whenever I've taught this course, in person, I always try to do as many graphs as possible. So I encourage it. All right. So sharing the screen. Okay, so this is 9-4 review. Is this what you were thinking?
Yes, so maybe number two,
All right,
the
let's
theta squared.
find the exact arc of the curve. Oh my God. Um, I have to remind myself how to do this. Give me a second here. I have a way I can do this. I'm not sure. You know what? I'm going to take a look. If you don't mind, I'm going to go into the affinity because I'm actually there's a way I can do it, but I think I want to make sure it's the way it's being taught. Give me a moment here. I apologize.
No worries. Take your time. Thank you.
So, yeah, oh yeah, geez. Yeah, it's okay. That's what I thought it was. All right. Um, so it's the same as in Cartesian. You have bounds. In fact, I forget what the bounds are. Oh, was it 0 to pi? I think it was 0 to pi.
Yeah, it was 0 to pi.
All right. So the general form is the Pythagorean form here. And it's going to be d theta. All right. So it's going to be 0 to pi. R is pi squared. So that squared is pi to the fourth. dr is 2 pi. I'm sorry, 2 theta. Quantity squared. So let's see what this gives us. And typical for arc length. Oh my, no, no. I have my limits of patience. Okay. Um, you can factor out a pi square. I keep on saying pi, a theta squared, and that'll just become a theta on the outside. And this gives you theta squared plus 4. Actually, okay, this one's not too bad. I was fearing we're gonna have to do a trig sub.
I think just a U sub.
Yeah, that makes it life up much nicer. So let u be theta squared plus 4. du is 2 theta d theta. So that means a 2 1/2. Now I'm going to ignore the bounds for a moment. I'm just going to worry about um, it's going to be rad u. And so 1/2, so 3/2, 2/3. So 1/3 u to the 3/2. And I'm just going to double check myself. So it should be 1/3 theta squared plus 4 to the 3/2. When I pop in the thing, I'm just going to do a real quick derivation. So the 3/2 comes down 1/2. Yeah, it looks good. All right. Now I'll go ahead and put back on the bounds. I'm back in theta. So I'll put on the bounds, pi and 0. You're just going to get some ugly numbers. You're going to get pi squared plus 4 to the 3/2. Take away, and then 0 just drops that out. That's 4 to the 3/2. The square root of 4 is 2. So that's actually 8. So it's 8/3. All right, so this one worked out. Um, it's not uncommon for these things to not work out. I mean, you can do the arc length, no problem. You can set up the integral, but a lot of times because of the radical, you get these impossible antiderivatives. This one worked out, so we got lucky. And I'm happy about that. Otherwise, we would have been stuck. But one thing you can do is just check by graphing. So check by, graphing or Desmos. So what you would do is you would actually type in this integral, just like you see it here. Use x, of course, and just see what it gives you and see if it matches this number.
Thank you. Yeah, the factoring out the theta squared, I was messing up. I was putting theta squared on the outside of the radical. So thank you.
Oh, okay. Yeah.
Yeah.
That was my first thought too. I was thinking, oh no, we're gonna have this ugly trig sub. But
That's
actually
what
it
I
turned
ended
out,
up with. So thank you. Thank you.
yeah, it turned out to be a nice U sub. So we're gonna do the same thing we did with the other arc length. We're gonna just set up a integral. The lower bound is 9/2 pi, top down to 7 pi. it's r squared plus the r d theta quantity squared d theta. So r squared, okay, I'm going to ignore the bounds for a moment. It's going to be 9e to the negative 2 theta. Now the derivative is going to be negative, so r prime is negative 3e to the negative theta. So when I square that, interestingly enough, I get 9e to the negative 2 theta. Okay, that's going to work out. Okay. Again, I was getting fearful this is going to be a nasty one. So what I really have here is basically I have 18e to the negative 2 theta. And the 18 is just really a constant. I'm going to bring it out in front. And I have square root of e to the negative 2 theta d theta. Does everybody see what I did there? I just do that just because it gets in the way. And it turns out that the radical and the square cancel. Now I haven't taken the integral yet, but I was able to work down, I was able to work the integral itself down to something tolerable. Okay. Now I can integrate that. I'll pop the bounds on at the end. So it's rad 18, and it's going to be negative e to the negative theta. And the bounds will be 7 pi for the top bound, 9/2 pi for the bottom bound. And this one is just going to be ugly. I don't think it cleans up at all. It's going to be negative e to the negative 7 pi minus negative, so that's going to be plus e to the negative 9/2 pi. And that's about as good as it's going to look. Okay. I thought it might get pretty, but apparently it does not. Yeah. All right. Again, I hope that helped. Does that help whoever else asked this one?
Yeah, it did, Professor. Thank you.
Sure. Go ahead and take an image if you want. Okay, I want to make sure I'm recording this. My bad. So this is 93 number 17. The curve is r equals sine of 2 theta. And we want the y coordinate of the highest point, which I assume is going to be the max, I guess. All right, so what we're going to do is we're going to convert this. So we're going to use that old trick that x is r cos theta, y is r sine theta. And that way we have, well, r is this guy, so sine of 2 theta cos theta, and y is this guy again, sine of 2 theta sine theta. Okay. And so we gotta, okay, so again, you don't want me to work out the whole question, but you wanted me to,
That's how I started to do it. Like that's what I was going to do as well.
uh-huh.
But then when I was looking at their work, it just seemed to go easier if you used the double angle for sine of 2 theta instead.
Yeah. Yeah, I'm looking at it too, because this kind of you have a lot of choices here. I'm seeing what they're doing. They did the double angle. What did they do that for? Oh, okay. So I guess it's because algebraically it can work out. So
Yeah, like if we do it the way you're about to start it, because that's how I started mine as well. Like I couldn't get to it. I couldn't finish it eventually. So like switching that to the double angle just made it easier, and then I was able to do it.
well, it would still work. You would actually take the derivative of this using the product rule. You would have you would actually have the sine of 2 theta and also the cosine of 2 theta appearing. You would actually have to swap those out at a later step for their corresponding double angle formulas. So I think it boils down to this is something where maybe they probably should have put a little tag in here saying it's easier to use the double angle formula. So the double angle formula for sine 2 theta is sine 2 sine theta cos theta. So that means y in its current form is 2, and then we have sine squared theta cos theta. That's just y. I haven't taken the derivative yet. Okay. I don't think you did anything wrong. I think your idea was sound. I think that if you just jumped right into it, so if you did dy over d theta,
Yeah, because we don't need to worry about dx d theta, right? Because we're just looking for the
right.
highest.
Yeah, we're looking for the horizontal tangents. If we were worried about like the farthest to the right, we would look at dx d theta because we'd be looking for vertical tangents. Um, I look at this too, and honestly, my first instinct would probably be just to jump right into it the way it's written, and it'll work. The problem is that when you take the derivative using sine of 2 theta, you still have an issue where you're going to have sine of 2 theta and cosine 2 theta somewhere in your derivative. And
And I think
unfortunately,
the issue was with setting it equal to 0.
yeah, because you want to boil it down to sines and cosines of just a single theta as much as possible. That way you can manipulate them algebraically. With 2 theta in here, it's almost like it's a different object. So you would have to make the conversion regardless. You either do it now or you do it later.
Okay.
I think they did it now, it would have been nice of them to put a note in there saying that's why they did it. Because I know sometimes Affinity just does things and doesn't really explain why they're doing it. This is just, yeah, this allows us by replacing, it gets rid of the sine of 2 theta. And suddenly I have sines and cosines of single thetas. That way, when I take the derivative, so like, let's do it real quick. So first times derivative second, which is negative sine theta, plus second, which is cos theta, times derivative. So that's going to be 4 sine theta cos theta. It looks kind of nasty for a moment. So I have 2 sine cubed theta plus 4 cos squared theta sine theta. As nasty as that looks, it's actually manipulatable because I'm only manipulating and moving around sine thetas or cos thetas. I don't have to worry about 2 thetas in there because that's like a whole different object at that point. I can bring out a 2. Actually, you know what? I can bring out a 2 and a sine theta. That leaves a negative sine squared theta and a 2 cos squared theta. At that point, we're in
That is like
business.
one of those double angles, like 2 cosine squared minus sine squared, I feel like is like cosine of 2 theta or something.
Yeah,
Like
but you know what? You don't have to necessarily do that. We can
because we're
actually
just
do,
setting equal to 0.
yeah, because we're just going to manipulate them. So I'll tell you what, sine of theta is 0. When is it 0? It's 0 at
0 and pi.
0 pi, 2 pi. Yep. So we'll keep that in mind. For this one right here, I'm going to write it. It's going to be sine squared theta plus 2 cos squared theta equals 0. I'll bring the sine over. So it gets rid of the negative sign. Divide out by cos squared. So I have 2 equals sine squared theta over cos squared theta. Well, that's actually tangent squared theta. So if I take the square root plus and minus, I get plus and minus rad 2 equals tan theta. Okay, sorry about that. And it's not a pretty number, but let's see what we get. I would have to do theta is arctangent of either rad 2 or arctangent of negative rad 2. You know what? Yeah, I don't think that's a common form. I think that's when
And
you're
it's
just,
not on the unit circle, so.
yeah, you have to punch that on a calculator. Um, yeah. Did you want me to go with it, or are you cool with that?
No, that's okay. I was just wondering if there was a faster way for this type of problem, or if I was
No,
just
not
something.
really.
Okay.
No. I think this is the fast way. Yeah, these just take time. All right, well, I'll leave it at that. Any again, any questions on this one? I kind of ran through it fast. All right. I'm gonna put it in the chat. So how do I do that? Oh, right there. I have all sorts of stuff. It's at my website, surgeon.net at math. Oh, went to the wrong. There you go. So if you want to look ahead at what you get in Math 267, I've been teaching the 267 for a number of years now, so I have a lot of materials on my website. So surgeon.net/math, and you'll see the 267 material right at the top. And yeah, definitely here, you know what? I got one more page. Surgeon.net math. Smiley face. There you go. For so you can get a little head start on what's ahead of you in 267.